Alright everybody, what's up? This video we're going to look at L'Hopital's rule, and we got a bunch of examples to work. Alright, so L'Hopital's rule says, suppose f and g are differentiable and g prime of x does not equal 0 on an open interval I that contains a, except possibly at the number a. Suppose that the limit of f of x and g of x as x goes to a are both 0, or the limit of f of x and g of x as x approaches a is equal to plus or minus infinity. Both of them are. Then the limit of f of x over g of x as x goes to a is equal to the limit of f prime of x over g prime of x as x goes to a. If the limit on the right exists or is infinity or negative infinity. So in other words, what that's saying is that if we're taking the limit and we plug the number in for x and we get 0 over 0, or we get infinity over infinity or negative infinity over negative infinity, then we can take the derivative of the numerator and we can take the derivative of the denominator. All right, and then evaluate the limit. So first, let's look at our examples. Like I said, we got a bunch of them to do. So let's get started. So I got the limit of natural log x over x minus 1 as x goes to 1. Now you can see, and if you're writing this down as I'm going over this, don't write this part down. I mean, you can, but write it off to the side. See, if we take the 1 and we plug it in, we get 0 over 0. All right, so we can apply L'Hopital's rule. All right, and hopefully you remember the natural log of 1 is 0. All right, so we can apply L'Hopital's rule. So that says the limit as x goes to 1, and the derivative of natural log is 1 over x, and then the derivative of x minus 1 is 1. And so that's the limit as x goes to 1 of 1 over x. All right, and now let's plug the 1 in. So that's just going to be 1 over 1, which is 1. And there's your answer. See, that's pretty easy. You got to know how to take derivatives. All right, let's look at the next one. All right, so we're taking the limit as x goes to infinity. So let's just look at it. So let's look at the numerator. As x goes to infinity, e to the x, that goes to infinity also, because we're taking e and raising it to a number that's getting larger and larger and larger, so the whole thing is getting larger. And then if we take a large number and plug it in for x down here in the denominator, well, that's a big number squared. That's going to infinity also. So we have infinity over infinity. So we can apply L'Hopital's rule. So that's going to be the limit as x goes to infinity of e to the x over 2x. Remember, derivative of e to the x is e to the x. All right, so let's see what we've got now. So as I take the limit as x goes to infinity, well, once again, the numerator is going to infinity. And let's look at the denominator. Well, as x gets larger and larger, 2 times a really, really big number, that's another really big number. So the denominator is going to infinity also. So we still have infinity over infinity. So I can apply L'Hopital's rule again. So that's the limit as x goes to infinity. Derivative of e to the x is e to the x. Derivative of 2x is 2. And so now, as I take the limit as x goes to infinity, well, this whole thing, I mean, this is just like a 1/2. So this is infinity. The numerator is going to infinity, and it's like infinity divided by 2. That's still out there at infinity. So this thing is infinity. All right. So hopefully all this is making sense for you. Okay, it's really not difficult to do. All right. Let me erase this and write it a little better. That's infinity. All right, so let's look at this. So we've got the limit of natural log x over the square root of x as x goes to infinity. All right, so what's the limit as x goes to infinity of natural log x? What would that be? Well, you remember what the graph of a logarithm looks like? It looks like this, doesn't it? So you can see as x goes to infinity, the y values are increasing. They're increasing slowly, but they are increasing. So the numerator's going to infinity. Now let's look at the denominator. Well, if I have a number out at infinity and I'm taking the square root of a number out at infinity, I still have a really big number. So you can see here we have infinity over infinity. So I can take the derivative of the numerator and denominator. So that's the limit as x goes to infinity. Derivative of natural log is 1 over x over, now I've got the derivative of square root of x. Okay. Now, I don't know if you've watched any of my other videos. If you haven't, watch them. There's a shortcut for finding the derivative of a square root. All right. So whenever we take the derivative of square root of x, we just take the square root. We do 2 times the square root of that. All right. And then up here in this numerator, the derivative of what's underneath the square root is just 1. Okay. If you don't understand how I did that shortcut, go search my channel for shortcut for finding the derivative of a square root. I believe that's what I named the video. Go watch it and it explains everything. Make your life a whole lot easier when you're taking derivatives of square roots. All right. And so now let's see what we've got. Well, first thing I think I want to do is I want to see if I can maybe simplify this sum. So this is going to be the limit as x goes to infinity. And that's going to be 1 over x divided by 1 over 2x to the 1/2. All right, so all I did, I just changed square root of x to 1/2 power. And so now this is going to be what? This is going to be limit as x goes to infinity of 1 over x times the reciprocal of this. So that's going to be 2x to the 1/2 over 1. And so now we can simplify this. That's going to be the limit as x goes to infinity. That's going to be 2 over x to the 1 minus 1/2, right? This x to the 1/2 comes down, subtract the exponents. So that's going to be the limit as x goes to infinity of 2 over x to the 1/2. And so now we look at this, we can see that the denominator is getting larger and larger and larger. The numerator is staying at 2, so that means it's going to 0. All right. So I hope everybody's following along. Okay. All right, so let's look at this one. All right, so we got the limit tangent x minus x over x cubed as x goes to 0. So, of course, first thing we want to try, plug the 0 in. Well, the tangent of 0 is 0, minus 0 is 0, and then 0 cubed is 0. So we've got 0 over 0. So let's apply L'Hopital's rule. So that's going to be the limit as x goes to 0 of secant squared x minus 1 over 3x squared. All right. Don't forget, derivative of tangent is secant squared. All right, let's plug the 0 in and see what happens. Well, secant of 0 is 1, right? Because remember, secant of 0 is 1 over cosine 0, which is 1 over 1, which is 1. And then, of course, it's squared, but 1 squared is 1. Okay? All right. So now, what happens? Well, we got 0 over 0 again. So we can use L'Hopital's rule again. So that's going to be the limit as x goes to 0. Now we got to take the derivative of secant squared x. So that's chain rule. Okay. Now what I'm going to do here first before I do that, I'm going to rewrite secant squared x. I'm going to write it like this so maybe it'll help you see it better. That's secant x squared minus 1 over 3x squared. Okay, so what did I do? Well, obviously when we got sine squared, cosine squared, secant squared, or whatever, we put the exponent right here. But remember, all that means that's just secant, all of it squared. Okay, you don't have to rewrite this step. I'm just doing this for you so you can see that I've got something in parentheses raised to a power. So I do the chain rule. So this is equal to the limit as x goes to 0. So the 2 comes down. Subtract 1 from the exponent, so that's secant to the first, okay, times the derivative of what's inside the parentheses here. So what's the derivative of secant? Well, that's secant tangent. And then the derivative of 1 is 0, and that's over 6x. Okay. All right. So now we've got the limit as x goes to 0 of secant squared x tangent x over 3x. So I just canceled the 2 and the 6, and I'm left with the 1 up here and the 3 in the denominator. All right, so now let's plug the 0 in. So I plug the 0 in, I get 0 over 0 again. Because remember, secant squared 0 is 1. Tangent of 0 is 0. So the numerator is 0 and the denominator is 0. So I could apply L'Hopital's rule a third time. But you know, I'm not so sure I want to do that. I mean, I could. It really wouldn't be that bad to do it, but look, if I'm applying L'Hopital's rule, I've got what? I've got the product rule, I got the chain rule in there, all that. So it might get kind of nasty. But like I said, if you want to apply L'Hopital's rule for the third time, nothing wrong with that. Okay, you can do it. Nothing wrong with it at all. But let's do it this way. Let's rewrite this thing. So I know if I plug 0 in for x on the secant squared, that's going to give me 1. So let's do this. Let's do 1/3 limit as x goes to 0 of secant squared x. Okay. Now I'm going to erase those parentheses. Well, there we go. Times the limit as x goes to 0 of tangent x over x. All right. So I just split it up. We can do that. Okay. Remember back when you first learned how to do limits? I know that was a long time ago. Okay. Back in chapter 2 in most calculus books. So this limit right here, I'm not really concerned about it because I mean I can just plug the 0 in, but if I plug the 0 in here it doesn't work. So what I can do is I can write this as 1/3. Well, let me come down here and make sure I have enough room. I can write this as 1/3 limit x goes to 0 of secant squared x times the limit as x goes to 0 of what? Sine x over cosine x over x. Right? And so this is 1/3 limit as x goes to 0 of secant squared x times the limit as x goes to 0 of sine x over x times cosine x. All right. So remember, that's x over 1, so it's this times the reciprocal of this, so it'd be this times 1 over x, and that's why that x is down there in the denominator. So now I've got 1/3 limit as x goes to 0 of secant squared x times the limit as x goes to 0 of sine x over x times the limit as x goes to 0 of 1 over cosine x. All right, so what just happened there? Why did I split it up like this? Well, do you remember back earlier in your calculus class that the limit of sine x over x as x goes to 0, that's 1? Remember, your teacher probably did a proof of it. All right. Well, I know if I plug 0 into here, that's going to make this 1. I know this is 1. And then if I plug 0 in here for x, then cosine of 0 is 1. 1 over 1 is 1. So that's 1 also. So I've got 1/3 times 1 times 1 times 1. And that is going to be what? Whoop, I got 2 equal signs there. That's going to be 1/3. There's your answer. All right, so that one was a little involved, but look what we got to do. We got to do a little bit of algebra. Well, algebra, a little bit multiplying fractions, and we worked with some trig identities, didn't we? See there? Manipulated some trig expressions. So, but like I said, if you wanna do L'Hopital's rule a third time, that's fine. And after going through all this, it might have been easier to do L'Hopital's rule a third time. I don't know, but I did want to work it like this to let you see more options. All right. So what about this one? So what I've found a lot is that once we cover the section on L'Hopital's rule, it seems like every time a student sees a fraction, bam, L'Hopital's rule. They'll do the derivative of the numerator, derivative of the denominator, and just keep going. But remember, what do? You want to always check to see if you can just plug this in and it works. Okay? So what's the sine of pi? And what's the cosine of pi? Well, let's pretend like you forgot. Okay? So if you forgot, I'm going to do this in a different color. So if you forgot, remember here's sine. That's 2 pi. That's pi. Here's cosine. Here's 2 pi. Here's pi. So we can see the sine of pi is 0. So that's going to be 0 over 1 minus, and we can see the cosine of pi is -1 minus -1. And so that's 0 over 2, which is 0. So you see, it's not that we didn't need L'Hopital's rule, it's we could not use L'Hopital's rule. Okay, in this problem, you can't use L'Hopital's rule because you don't have 0 over 0 or one of the infinities over infinity. Okay, so if you tried to do L'Hopital's rule there, you would be wrong. Okay, so just remember, before you apply L'Hopital's rule, plug that in and see if you can use L'Hopital's rule. All right, so let's look at this one. We got the limit of x times natural log x. And I left this off the problem, coming in from the right. All right. So we've got the limit as x goes to 0 from the right. So if I plug 0 in for x, that's 0. Well, I can't plug the 0 in for x on natural log because natural log of 0 is undefined. Can't do it. So let's figure out what's going on here. So if I look at the graph of natural log, that looks like this. And you can see as I'm coming into 0 from the right hand side, natural log is going to negative infinity. All right. So I've got 0 times negative infinity. And please do not put 0 as your answer. I mean, that may be the answer, but it's not 0 because it's 0 times negative infinity. That's not what's making it 0. You cannot do that. All right. So we've got 0 times negative infinity, which we can't have that. So let's see if we can rewrite this thing maybe. Okay, see if we can rewrite this thing to see if we can't get it in the form where we can apply L'Hopital's rule. Okay, so I'm going to rewrite this as the natural log as x goes to 0 from the right of natural log x over 1 over x. All right, so how in the world did I get that? Well, let me just show you here. So natural log of x over 1 over x, well, that's equal to the natural log of x times the reciprocal of the denominator, right? So times x over 1, which is x natural log x. See, it's this. So I just rewrote this into this form. So why did I do that? Well, as x comes to 0 from the right-hand side, well, I just showed you natural log of x goes to negative infinity. And then as x comes to 0 from the right of 1 over x, well, the denominator is getting really, really small, like 0.1, 0.0001. So I have 1 over a really small number. So this one's going to infinity. So I've got negative infinity over positive infinity. So I can apply L'Hopital's rule. And so this is the limit as x goes to 0 from the right. The derivative of natural log is 1 over x. The derivative of 1 over x is negative 1 over x squared. Okay. Remember, taking the derivative of 1 over x, that's the same thing as x to the negative 1. Then just use the power rule. And so then that's going to give me the limit as x goes to 0 from the right of 1 over x times negative what? X squared times the reciprocal of this. And so that's going to equal what? The limit as x goes to 0 from the right of negative x. And so this is negative 0, which is 0. Okay? So if you were to have, if you had this problem on a test and you looked at this thing and you said, oh, 0 times negative infinity, that equals 0. If you were to have done that on the test, and let's say you didn't have all of this work right here and you just had the 0 stuck there, if you're in my class, if the problem was worth, say, 8 points, I would have taken off 8 points for that. Okay? And I'm sure most other teachers would have also. Okay? So be aware of that. All right, so let's look at this one. So how about this one? All right, so the limit as x goes to 1 from the right of 1 over natural log x minus 1 over x minus 1. All right, so as x goes to 1 from the right, this first term right here, that goes to infinity, and this last term goes to infinity. So infinity minus infinity, that's 0, right? Wrong. You can't do that either. All right. So let's look at what we can do. So how do I know that this one goes to 0, this first term? Well, once again, look at the graph of natural log. There's 1. So as I'm getting closer and closer to 1 from the right hand side, you can see the y values are getting closer and closer to 0. So I've got 1 over something that's really small, that's infinity. And same thing here, as x goes to 1 from the right. I mean, you're looking at numbers like 1.0001 minus 1. That's a small number, so that goes to infinity also. So what in the world do we do here? Well, let's get a common denominator, see what happens. So this is going to be the limit as x goes to 1 from the right. And the common denominator is x minus 1 times natural log x minus 1, natural log x. And so this one's going to be x minus 1. This is going to be natural log x. And so that's going to be the limit as x goes to 1 from the right of x minus 1 minus natural log x over x minus 1 times natural log x. So let's see what happens here. Well, look at that. That's going to give me 0 over 0. See that? If I plug the 1 in, 1 minus 1 is 0. Natural log of 1 is 0. 0 in the numerator. Here, 1 minus 1 is 0. Natural log of 1 is 0. 0 over 0. I get 0 over 0. So look at that. We can apply L'Hopital's rule. So that's going to give me the limit as x goes to, well, let me come down here and do it. Make sure I have enough room. So I've got the limit as x goes to 1 from the right, and that's going to be 1 minus 1 over x. That's the derivative of the numerator. Derivative of the denominator, that's product rule. So that's going to be 1 times natural log x. Remember, derivative of the first function times the second function, plus the derivative of the second function times the first function. All right, so what happens here? Well, look at there. We get 0 over 0 again, don't we? But, before we do that, because we get 0 over 0, I'm going to have to take the derivative again. So let's see about cleaning this up a little bit, simplifying it some. So remember, to simplify this, I'm just going to multiply each term by x. And so that's going to leave me with the limit as x goes to 1 from the right. That's going to be x minus 1, right, over x natural log x plus x minus 1. So, and you can see 1 minus 1 is 0. Natural log of 1 is 0, so that's 0, and 1 minus 1 is 0. So I get 0 over 0 again. So we can apply L'Hopital's rule again. So I'm going to get limit as x goes to 1 from the right of 1 over. Now on this first part, I'll be using the product rule. So that's the derivative of the first function times the second function plus the derivative of the second function times the first function plus 1. And so that's the limit as x goes to 1 from the right of 1 over, that's going to be natural log x plus 2, right? So that's 1 right there. See, that's 1. 1 plus 1 is 2. Now let's plug the 1 in. So that's going to be 1 over natural log 1 plus 2. That natural log of 1 is 0, so we get 1/2. All right. So that problem had to do a little bit of algebra there. Okay. Not bad. It's not too bad. All right. So let's look at this one. We got 11 problems total to work. If you're sitting there wondering when in the world is he going to finish? All right. But you need to watch them all so you'll learn something. All right. So we got the limit e to the x minus x as x goes to infinity. So once again, x goes to infinity, this goes to infinity, this term goes to infinity. Infinity minus infinity, of course, is not 0. All right, so what can we do here? Well, there's some things that we can do. We know that e to the x, that's going to infinity a lot faster than that x is. So I'm guessing the limit's probably going to be infinity. But let's see what we can do about that. So this limit as x goes to infinity, I'm going to factor out x, and that's going to leave me with e to the x over x minus 1. See that? And so looking at this, what's going to happen? Well, I need to take a look at this part right here. See that? This e to the x over x. Well, if I used L'Hopital's rule on that, the limit as x goes to infinity of e to the x over x, and that's infinity over infinity, which is the limit as x goes to infinity, and that's going to be what? E to the x over 1. So we can see that's this term right here is going to go to infinity. That 1, it's insignificant. I mean, infinity minus 1. No, I mean, what's that 1 doing? Nothing. So we can see this term is going to infinity. This one's going to infinity. So it's like we have a really big number times another really big number. Well, what's that going to do if you multiply two really big numbers together? You're going to get even a bigger number. So we can say that's going to infinity. All right. All right, let's look at this one. The limit secant x minus tangent x is x goes to pi over 2 from the left. All right. So how do we do this? Well, first we need to really kind of see what's going on, don't we? What do we have? Well, you can do that by, let's sketch the graph of each of them. There's negative pi over 2, right? There's pi over 2, and we know tangent looks like this. So you can see as I'm coming into pi over 2 from the left, this thing right here is going to infinity. Tangent's going to infinity. Now what about secant? Well, hopefully you still remember how to graph secant. All right. There's 1, negative 1. And how do we graph secant? Well, we're going to dot in cosine, right? We're going to dot in the cosine. So I got my vertical asymptotes here and here. All right, so we sketch in cosine. There it is. Okay, and as we come into pi over 2 from the left-hand side, it's going to infinity also. See that? So we've got infinity minus infinity, which we know by now is not 0. Okay, I mean it could be, but we can't say it's 0 because of that. All right, so what do we do here? What are we going to do? Well, what did you do in trig when you were simplifying trig identities? When you had to simplify something, most of the time you would just rewrite everything in terms of sine and cosine, right? Let's try that. Usually that doesn't fail us. So I've got the limit as x goes to pi over 2 from the left of 1 over cosine x minus sine x over cosine x. And so that's going to be the limit as x goes to pi over 2 from the left of 1 minus sine x over cosine x. So let's see what we get. The sine of pi over 2, what is that? That's 1, right? Remember, there's sine, there's cosine, there's pi over 2, there's pi over 2, right? So the sine of pi over 2 is 1, so that's 1 minus 1 is 0. Cosine of pi over 2 is 0. Look at that, I got 0 over 0. L'Hopital's rule. So here we go. The limit as x goes to pi over 2 from the left. That's going to be what? Negative cosine x over negative sine x. And let's see what happens. Well, let's see. Well, remember, well, dang it, I erased it, didn't I? There's pi over 2 for cosine. Let's just put it back up here so you can see it. There's pi over 2 for sine. So I've got what? That's 0 over 1, right? Negative cosine of pi over 2 over negative sine pi over 2 is 0 over 1, which is 0. There's your answer. All right, see, stuff's not bad, not bad. All right, now we got 2 more to do, and we'll be done. Okay, don't leave on me now. You've come this far, you might as well watch the rest of it. Okay. All right, so let's see what we've got here. All right, so this one, if I plug the 0 in, the sine of 0 is what? 0. Okay. So I've got 1 minus 0 is 1. So I've got 1 raised to the, well, what's cotangent of 0? Well, do we remember the graph of cotangent? There's a vertical asymptote there and there at pi. And so cotangent's going to look like this. So as I come into 0 from the right, cotangent's going to infinity. So I got 1 raised to the infinity. Is that 1? I'm going to let you take a guess on that. And if you said no, then you would be correct. Okay? We cannot say 1 raised to the infinity is 1. Okay? You can't do that. And there's different types of indeterminate powers that you might get. I'll just write them right up here. You may get 0 to the 0. You may get infinity to the 0, and you may get 1 to the infinity. Okay? So these are all indeterminate forms. All right? This raised to the 0 and this raised to the 0, that's not 1. Okay? So how in the world do we work this? Well, let me show you. So we're going to start out and we're going to say let y equal 1 plus sine of 4x. I'm going to let y equal whatever this is. All right? Well, I'm sorry. I'm going to let y equal not what's in the parentheses. I meant to say the whole thing. That's what I'm going to let y equal. So now what I'm going to do is I'm going to take the natural log of both sides. All right. Now, why did I do that? Well, let's look at it. That's going to allow me to get this exponent out of there, because this is equal to what? Cotangent x times natural log 1 plus sine 4x. Remember that? Remember that property you have that says you can pull the exponent down in front of the natural log? Okay. So doing this, what do you think I might be trying to do here? Well, I'm going to try and see if I can get this in L'Hopital, in the form where I can apply L'Hopital's rule. Okay. So we know that as x goes to 0 from the right, and yes, I realize I have not written limit down. I haven't done the limit yet. I'm just rewriting this, and then I promise you I'm going to take the limit of this. So remember, cotangent x as x went to 0 from the right, remember that was infinity, and this was what? That was 1, right? But the natural log of 1 is 0. So I got 0 times infinity. And we know from previous experience that we've had in this video that doesn't mean it's 0. But I could rewrite this thing as what? Natural log 1 plus sine 4x over tangent x. All right, so what did that do? Well, let's look. If I'm taking the limit as x approaches 0 from the right, well, if I plug 0 in here, that's 0. If I plug 0 in here, that's 0. I've got 0 over 0. So I could apply L'Hopital's rule to that. All right. So now, what I want to do, okay, so remember I got 0 over 0. So what I want to do now is I'm going to take the limit. I'm going to take the limit as x goes to 0 from the right of natural log y. Now, why am I doing the natural log of y? Why not just y? Well, you'll see in a minute. Okay, just hang in there with me on this problem. So this is equal to the limit as x goes to 0 from the right of natural log 1 plus sine 4x over tangent x. All right. So once again, we just discussed that I've got 0 over 0, so I can apply L'Hopital's rule. And so this is the limit as x goes to 0 from the right, and the derivative of the numerator, that's 1 plus sine 4x, and then the derivative of that, well, derivative of natural log, remember that goes in the denominator, derivative of this goes in the numerator, so that's going to be 4 cosine 4x over, and then the derivative of tangent is secant squared x. All right, now I could go and simplify this thing and all that good stuff, or I can just see that the cosine of 0 is 1, right? And so that's going to give me 4 over. And then the sine of 0 is 0, so that's 1 plus 0 is 1. And then secant of 0, that's 1, and so this is going to give me 4. All right? So you might be thinking, okay, so what? Big deal. Well, let's look at it. Now let's take the limit as x goes to 0 from the right of our problem. So I'm just going to rewrite this again. That's going to be 1 plus sine 4x raised to the cotangent x. All right. Well, this is equal to what? The limit as x goes to 0 from the right of y. All right. Because didn't I say let y equal this? All right. All right. So pay attention here. Pay attention. So this is equal to the limit as x goes to 0 from the right of what? E raised to the natural log of y. Now, where in the world did that come from? Well, do you remember there's a property that says b to the log of x with base b is equal to x. So remember, if the base of the exponent and the base of the log are the same, then your answer is what you're taking the log of. And isn't e to the natural log y, isn't that the same thing as e to the log of y with base e? Remember, natural log is log base e. See, this and this are the same. Your answer is y. It's just a different way to write y. Okay? Now, maybe you figured it out. I don't know. But look at this. I'm taking the limit of this raised to the natural log of y as x approaches 0 from the right. Well, natural log of y, what would that be? Well, look at here. You see this? That's 4. And so this is e to the 4th. And there's your answer. All right. Yeah, that one's, that's how you do those. Okay. You've got the procedure to work them now. All right. You know how to work them now. All right. Let's look at this one. All right. So this one's 0 raised to the 0. So that's, that's what? See, the forms indeterminate forms I wrote down for you. See, this number 10, that was 1 to the infinity. This one, 0 to the 0. And that's what we've got here, 0 raised to the 0. Now, we could go and we could work this problem exactly like we did the other one. Okay? We can do it exactly like we did the other problem. Or we could do what? Well, let me show you this. If you notice these kind of things, sometimes you can make the problem easier to work. Okay. So I could write this as the limit. And you might be thinking when I work it this way, well, how in the world did you know how to do that? Practice. Okay, you work these things, and that's why I'm showing you, so you can look out for things like this and say, hey, can I do this? Okay, so I could rewrite this as what? E to the natural log of x, right? That's going to give me the x right here. You see that? That's going to give me that x. Because see, e to the natural log of x is x. And then that is raised to the x power. Now, I don't know if you see it now. I hope you do. I don't know, but let's keep going. So that's going to be the limit as x goes to 0 from the right of e to the x times natural log x. All right, you see that? And now we can take the limit of x times natural log x. Can't we do that? Look. Let me see if I can go back up here. Look at that. See, we worked it right there. All right. So if you've been taking notes this whole time, just go back to example 6. If you're not taking notes, rewind the video and watch it. That's what we would do with that exponent. And what do we get as an answer? We get 0. All right. So this is what? E to the 0, which is 1. And there's your answer. All right. So now, just for fun, okay, just for fun, we're almost about 50 minutes into the video. I actually thought this video would be a lot longer. But let's do this problem again. How about that? The limit as x goes to 0 from the right of x to the x Okay, let's do it like we did number 10. Okay, look, you're getting bonus here, getting bonus coverage. All right, so I'm going to let y equal x to the x. So natural log y is equal to the natural log of x, right, raised to the x. Well, let's write it like this. I just took the natural log of both sides. And don't we have a property that says we can take the x and pull it down in front? So that's x natural log x. And so now I'm going to do what? Take the limit as x goes to 0 from the right of natural log y is equal to the limit as x goes to 0 from the right of x natural log x. And look, see, that's exactly what that is. That problem 6, see, we'd be taking the limit of that, taking the limit of this, and we know that's 0. Okay, let's not work problem 6 again, but that's 0. And so now we've got the limit as x goes to 0 from the right of x to the x, right, is equal to the limit as x goes to 0 of what? Of y. See, look, I'm doing it just like I did, where am I? Just like I did this problem here. See, taking the limit of our problem, substituting it for y, and then I'm going to do this. Okay. See, I let y equal this. And so I changed this to y. And so now this is what the limit, that's from the right, x goes to 0 from the right of what? E to the natural log y, which is what? E to the, what's the limit of natural log y? 0. Okay, so you get the same answer either way. I think this is a little bit easier. Okay, if you can recognize that stuff. But you know, in order to do that, you've got to practice it, do your homework, and all that stuff. But yeah, you know, there's 2 different ways we did that one. We did it that way, and then of course the other way is like we did problem number 10, the previous problem. All right, so I hope that helped. Got a good understanding of L'Hopital's rule now, and you can see it's a bunch of rewriting and all that stuff. So hopefully it helped. I appreciate you watching. I hope you stuck around for the whole video. Give me a like, share, subscribe. Thanks for watching, and I'll see you in the next video. Later.